So we have this 141 of Leetcode linked list cycle, and the question simply says that you'll be given the head of a linked list and to determine if it is a circular linked list or not. Let's take an example. Let's say you have a linked list like this, right? Now, clearly this linked list is circular, and if it is a circular, you need to return true, and if it is not circular linked list, you need to return false, right? Now, first look at the time constraint. Now, in the constraint section, we are given the number of node in a linked list is ranging from 0 to 10 raised to the power 4. So let's say if number of node is 10 raised to the power 4, what is the maximum time complexity that we can have? Let's say UN. And no, first let me talk about the basics. Let's say 1 second in C++ lead code, we can have at most 10 raised to the power 6 operations, right? Now, so if we have a time complexity of ON, which would be simply O 10 raised to the power 4, this will be less than 1 second, right? As it is less than O of 10 raised to the power 6, right? If it is like this, O of 10 raised to the power 6. So this will, if this is under 1 second, this will be also under 1 second. So first you need to remember the table, right? And time complexity table always, if you don't write it down, right? O of n factorial greater than O of 2 raised to the power n. Now these are the time complexities, right? Time complexity order table. This has the maximum time complexity of n factorial, and then followed by 2 raised to the power n, O of n raised to the power 4, O of n cube, O of n square, O of n log n. And you can also follow here O of n log n, log of n. Then O of n, O of log n, and O of 1, right? Now, to make it simple, let's ignore this one. This is a general basic time complexity table. Now, you clearly saw that O of n lies under the time complexity, like the time bracket, that this can execute under 1 second. If O of n can execute under 1 second, then O of log n will also execute under 1 second. Similarly, O of 1. So all of these values, all of these time complexities will never get us TLE. Now let us look at, let's say O(n) square. Let's look at O(n) square. If n is 10 raised to the power 4, n square will be 10 raised to the power 8. So clearly 10 raised to the power 8 is greater than 10 raised to the power 6. So it will never run under 1 second. So this is eliminated. Now let's look at n log n. Now n log n, let's say n log of n. What was the value of n initially? The maximum node that we can have, 10 raised to the power 4. So 10 raised to the power 4 into log of 10 raised to the power 4, right? Log of 10 raised to the power 4 is for 4 times 10 raised to the power 4. 4 times 10 raised to the power 4 is less than 10 raised to the power 6. So this will execute under 1 second. So basically, we can have all of these time complexities of this code and not get a TLE, right? Any of these, let's say, let me just, if you write a correct code and your time complexity of the code lies in this range, you will definitely get a TLE. Even if your code runs perfect, it will give you TLE. That is, it will not execute under a second. And your answer would be wrong. You have to somehow make your code run under this time complexities, right? The maximum that you can have is n log for this, even if for the brute force. Now, we will look at 2 methods to solve this question. Before we'll discuss the brute force way, right? The brute force way and the optimal way. In the optimal way, we will simply use pointer and definite an algorithm is given, the fast and slow pointer, and another word, Floyd cycle detection. This will be our optimal way. And now, before getting to the brute force way, let us look at some C++ containers that we generally use. We have unordered map, unordered set, map and set. Now in unordered map and unordered set, the insertion, deletion, searching, all of this takes a time complexity of O of 1, right? O of 1. And but there is a catch to it. There is something called as hash collisions, right? Hash collisions. Generally, it doesn't happen, but if it happens, because of hash collisions, the time complexities can go up to O of n, right? Generally, it doesn't happen actually. Generally, the time complexity stays O of 1, but because of hash collision, it can go up to O of n. Now, for the map and set, all of this, the time complexity stays O of log n. Like O of log n, right? Now, there is a clear difference that you can clearly see. Key the best time complexity over here is O of 1, smaller than O of log n, smaller than O of n, right? Now, my suggestion would be key. Every single time you are asked to implement a map or a set, try implementing an ordered map and unordered set, right? And if by luck, if you get a TLE, that means you are getting an hash collision or something like that. Shift back to map and set. Probably you will not ever get a TLE after that. Try implementing an ordered map and unordered set because it is going to save you a lot of time as it is executing under O of 1 time complexity. Now, let us discuss the brute force way of solving this problem. The brute force way was, let's say you are given a linked list. Let's say let's say this is a linear linked list and this is a circular linked list that you are given, right? Now, you need to return false over here and true over here. This is a brute force way. Now, you can clearly see in a non-linear, a non-circular linked list, you will every single time will reach a null. So this would be our first condition. If you get a null, right? If you start from the head, and if you get a null, this is simply you need to return false. In a circular linked list, the basic idea that I can generally have is that you can get different nodes that repeats more than once. Let's say you start from the head, go on iterating. If you look at this node, you get it, you visit it once, then you go in a loop and visit it twice, thrice, right? There are different nodes that visited multiple times. So basic idea is that you take any container, you can use a map or a set. Let's say we are using a map, right? Let's say we are using a map. Now, what we can have is we can store all of these nodes into the map, or you can also use a set, no problem. You can store all of these node into a map. Every single time you iterate, like you have this temp over here and you keep on moving the temp and storing it into the map, right? Let's say you go on and store the first node into the okay, this is not first node actually. You stored the initially first node. Let's number this one 1 2 3 4 5, and you need to keep in mind we are actually storing the address, not the value. Values can repeat but address cannot. Address and value, you don't store the value, you also only store the address. So our maps data type would be node type, right? Not integer. Now you go on iterating over it, store the first node, right? Then you go on iterating over, store the second node, the third, fourth. When you are here, when the temp is here, you store the fifth node, right? Now fifth next is 3. If you are going to store 3, it is already present, and if the node is already present, then you will simply return true. Why? Because a node is getting repeated twice. So this is our understanding key. When you are trying to push a node into a container, try searching that node in the map or a set key if it is present or not. If it is not present, then push the node and move the temp to the next node, right? And if it is present, simply return true. So everything that I said is I'm going to write it down. Let's say what is the first thing that we did was initializing temp to head, right? Initializing. This is a brute force way actually that I'm writing. It is going to take an extra space complexity as well, and also a time complexity. Now, first we are taking a temp variable and storing it, a temp pointer, and storing it in the head, right? So it is now pointing to head. Now we are going to run a loop, right? Now the loop condition should be while the temp which is at the head should not be equal to null. Now as it reaches null, let's say the condition will be while temp not equal to null. Now outside this while condition, if the temp is null, That means we are sure that this is not a circular linked list. So we'll return false. Outside the while loop, we can simply write return false. Now, inside while loop, what we will do is each and every node we will take with the help of temp, we'll first check if it is present in the map or not. And if it is present, we'll simply return true, because a node which is present and visited once again, we can confirm that this is a circular linked list. Now, if it is not present, we'll simply push it into the map. First statement will be if MPP, the name of the map, let's say we create an ordered map. As I told you, first create an ordered map. If it gives you TLE, shift to map, right? The type should be null, and let's name it MPP, right? Now MPP dot find the temp, right? If we found the temp not equal to MPP dot end, that means we found it inside the map, then we will simply return true. Else what we will do is we'll push the temp into the map. So MPP temp plus plus. You could actually write a plus plus or put any constant or put any values to it. Value does not matter. All it matters is the key. Yeah. Plus plus simply means the default value was initially 0. So it will be 1, right? You push a node along with the value 1, 1, 1 and 1. We check if it is present or not. And if it is present, simply return true. Else just push it into the map. Now after pushing it into map, we need to actually shift the temp, right? So we'll write temp equals to temp next. So this is our code for the brute force way of implementing or checking if a loop is present in a linked list or not. Now talking about the time complexity, first we are running a while loop over, this is the while loop, right? We are running a while loop over the whole linked list. So it will be obviously on, and then there are inner statements of mpp.find and mpp.end, and we are inserting it and checking it in the map. Now, for unordered map, as I told you, insertion, deletion, and searching takes O of 1. For the worst case, it will take O of n, right? And we are assuming the worst case does not happen, and we're taking O of 1. We are executing 2 of this statement, so it will be 2 of 1. Now, this is for unordered set or unordered map, right? Now, if this gives you TLE, what I told you is that shift to set or a map. Now, in set or a map, the time complexity will be n into n is the number of times you're iterating over the n is the like one iteration over the linked list, right? And then searching and insertion into the map takes a time complexity of log n. So 2 times log n. This will be the time complexity in set or the map, right? Now talking about the space complexity, both of the implementation, the space complexity will be O of n, as we are implementing taking the worst time space complexity, implementing a map or a set, taken the space complexity O of n. Now we are going to discuss the optimal method. The optimal method does not include any of the space complexity. It will be of O1. It's called fast and slow pointer, also known as Floyd Cycle Detection. Detection. Now, in this optimal method, what we do is that, let's say this is the linked list that we are given. Now, we assign 2 pointers to the head. One is the fast pointer, and another is the slow pointer, right? Let me write in different colors. Let's say one is the fast pointer, another is the slow pointer, right? And one simple rule is that you move slow pointer once and the fast pointer twice, right? So you move in the first iteration, you move slow once and you move fast twice. So fast pointer is here. Again, in the second iteration, you move slow here and fast goes here. Again, you move slow here and fast goes here. Slow here and fast will be here. And you keep doing it, right? you have to keep doing it until fast and slow is on the same node, right? So slow is here and fast will be here. Again, slow is here, fast will be right here. Erase all of these things. Now slow is here, right? And fast will move here. And we clearly stop right this place, right? We can clearly see fast and slow pointer is at the same node, and we can simply return, right? Now, for let's say this was for the circular linked list. What if we had a non-circular linked list? If this was a non-circular linked list, let's say this is the example, it hits null. We take for the even and odd case both. This is for the even case, the even number of nodes. And let's take for the odd case. Let's say we have 5 nodes. 1, 2, 3, 4, 5. Null. Now, we assign the fast and slow pointer here. Move the slow pointer by 1, fast pointer by 2. Slow pointer by 1, fast pointer by 2. For the even case, fast reaches null. So, fast reaches null, right? And for the odd, fast and slow is assigned here. Slow moves 1, fast moves by 2. Slow moves 1, fast moves by 2. Slow moves 1. And you cannot move fast any further. So, fast will reach one step before null at the last node. So, fast dot next will be null. This should be our condition. This is the two condition that we will achieve if we don't have a circular linked list. So this should be our, the while loops condition. So we will have any non-circular linked list. If you take, either the fast will reach null or the fast next will reach null. Both of the conditions should be satisfied to accompany even and odd cases. So our condition will be while fast pointer is not equal to null, right? And fast pointer dot next, fast pointer is not at the last node, right? We will never, if you look at the circular linked list over here, we will never get to the last node, right? There is no last. We can keep on iterating over and over, right? But in a non-circular linked list, we can reach actually null and one step before null. So this should be our breaking condition. While fast pointer is not equal to null and fast next pointer is not equal to null. This simply means that we are not at null and we are also not at the last node. Then execute some statements. What are the two conditions we had? The slow pointer moves by one step, slow, next, and the fast pointer moves by 2 steps, fast, next by 1 and by 2, right? Now, what was the breaking condition in a circular linked list, right? If a non-circular, we are checking for non-circular linked list by this while statement, it is not at null and it is not also at the last node. But what should be the breaking condition for the circular linked list? That fast and slow pointer cannot be at the same node. So write the same condition over here. If fast equals to slow, simply return now, right? And this is our while condition. And outside this, simply write return false. Why? Because if this while condition fails, we can be assured that this is not a circular linked list. We will simply return false. Now, I will tell you the mathematical intuition behind it, right? Let's say this is the circular linked list that we are given, and the fast and slow pointer is at the head. Now the question arises, we saw that in a circular linked list, at some point of iteration, the fast and slow pointer intersect at one node, and then we return true, right? Now, what if a fast and slow pointer never intersect? It can possibly be, right? A slow pointer is here and fast is here and fast goes over the slow. Mathematically, I will actually prove you that fast pointer and slow pointer in a circular linked list of iteration is bound to intersect, right? Now, if you perform the iteration of fast and slow and keep track of the distance from fast to slow, you would be able to understand. Now, let's take an example. Ki slow moves by 1 and fast moves by 2, right? Now, once fast and slow pointer enters the circle, enters any of the loop. Now, we clearly see that fast and slow pointer is inside a loop. Now, take the distance from the fast pointer to the slow pointer, right? Now, the distance is 1. Count the number of nodes between them, right? 1, 2, 3, 4, 5, 6, 7, right? Count the jump. It's 7. Now, move the slow pointer by 1 and fast by 2. Again, now the distance is 1, 2, 3, 4, 5, 6. Again, move the slow by 1 and fast by 2. Now the distance becomes 5, right? Again, move the slow by 1 and fast by 2. The distance is 1, 2, 3, 4. Right? You can clearly see a pattern that every single time you're iterating, the distance is decreasing by 1. Right? Let me delete the... Now again, move the slow by 1. Slow moves by 1. Fast moves by 2. 1, 2. Right? Now, 1, the distance between fast and slow from the first is 1, 2, 3. Right? Distance is 3. Again, move the slow by 1. Fast by 2. Now the distance is 2. Right? You can clearly see it keeps on decreasing. Now move the slow by 1 and fast by 2. 1, 2. Right? Now the distance is 1 between them. Fast and slow pointer, the distance is 1. We erase all of this. Now, finally, you move the slow pointer by 1 and fast by 2. And you can clearly see that it intersects in one node and we return true. Right? This is a circular linked list. And the distance is 0. No matter where you start, right? Whatever node you start, once the slow pointer and the fast pointer gets into a loop, right? Let's say this was your linked list and it gets slow pointer is here and fast is here. Slow and fast pointer is bound to collide into a single node. Now let's talk about the time complexity of the above code. Right? Now, time complexity. What if we have a non-circular linked list, right? We at the end reach null. So it will iterate over O(n) time, right? Now, for the circular linked list also, it will actually iterate over O(n) time. I will show you a beautiful pattern that we have here. Now, how many iterations did we perform in here? We have the total number of node is, the n value is 1, 2, 3, 4, 5, 6, 7, 8, 9, right? N value is 9. But count the number of node in the loop, right? 1, 2, 3, 4, 5, 6, 7, 8. N is 8. This is the number of node in a circle, like this portion of it, right? Now, if you count the number of iterations that we had to perform to confirm that this is a circular linked list is also 8, from 7 to 0. Now, the basic idea is that let's say we have a linked list. We start from here, there's a linear part, and then comes the circular part. The idea is the number of node that we are going to have in the circular part will be the time complexity of the optimal code. Let's say the number of node here was x and the number of node here was y. Then the time complexity will be O of y, right? So initially at max, the number of node that we can have is n equals to 10 raised to the power 4. Now now what if all the nodes are in circle, right? We start from the circle and all the 10 raised to the power 4 nodes can be in circle. Now this could be the maximum time complexity would be O of n, O of 10 raised to the power 4, that is O of n. For the circular part and for the non-circular part, the time complexity will be O of n. Now for the space complexity, it will simply be O of 1 because we are not using any extra space.